Okay, today we're covering section 3.4, linear programming. The idea is we have a set of equations that are our constraints. This equation says we can't be more or less than that. This equation says we have to be less than this. This equation says we have to be more than that. Those are our constraints. They decide our parameters of what we're dealing with. The last part of your notes, you'll kind of see where it's applied. We actually work a couple of problems, how to make it happen. The last one is where you see where it will actually be applied somehow. Okay, where it makes sense. It will kind of make sense when we get to that last part. The constraints are our limits. Those are equations that will describe our constraints. Feasible region is everything inside. So all of our constraints, they're inequalities. And so we'll be graphing a system of inequalities, but lots of inequalities. And the feasible region is the area that is contained within all of those inequalities. Similar to what we were doing at the end of the week last week, where you had the overlapped area, same idea, only this is a more contained area. Vertices are the corners, points of the feasible region, one of which is the max, the other one is the minimum. Each vertex, going back to your geometry days, each vertex of the region will have an xy coordinate. That xy coordinate will either give it, is the only place where we will find our maximum value or our minimum value. And what are we trying to maximize or minimize? That is a particular function, an objective function. And you'll see as we go along, this kind of makes a little more sense as we're doing stuff. Okay, any questions so far? Okay, so here we are. This is the situation we have. Given the following constraints, graph a feasible region and evaluate the objective function for its maximum and minimum values. So these are our constraints. We're going to graph each one of those individually, find the region that they work as a whole, and that's our feasible region. Now, when we were doing a system of inequalities, because that's what our constraints are a system of inequalities. When we did this last week, we shaded the half and we shaded this half. You do not want to do that here. When you do your inequality, you want to find you want to only shade just like one side of the line that you have. Okay, it's really kind of important that you do that. And you want to graph very carefully when you do this. So, first one I want to do is I want to graph the first equation, 2x plus 3y is less than or equal to 21. So I get my y-intercept is 7. 1, 2, 5, 6, 7. Is that right? 1, 2, 3, 4, 5, 6, 7. Okay. And then my x-intercept is 10.5. I don't know if I have 10.5 on my x-axis or not. 1, 2, 3, 4, 6, 7, 8, 9, 10.5. And I really have to try to do this well. Let's see if this screws this up. Boy, that didn't do much of anything. I know there's a way to draw lines. I'm really not worried. So that's my first equation. Okay. And once again, I do have to test. So I want to test the origin. Put in 0 plus 0. Is 0 less than 21? It is. So that means I want everything less than this line. I don't want anything more. I want everything less than that line. Okay. Do my next one. Okay. My y-intercept is 2. I can do that. But my x-intercept is -2, and I don't have -2 to graph for my x-intercept. That won't work on this one. So I have to rearrange because I don't have my full area. I don't have a full graph. I only have positive x's and positive y's. So in order to graph this, I actually need to rearrange it, subtract the x from both sides, multiply everything times -1. I get y is less than or equal to x plus 2. That's what I'll have when I rearrange that one. So I have y-intercept here. My slope is 1. Okay. And I want to test a point. I can pick the origin. 0 minus 0 is greater than -2. It works. So it's everything on this side of the line. Okay, x is less than or equal to 6. That's an easy one to do. 1, 2, 5, 6. And I want everything less than that. Now my other two constraints are what? X is greater than or equal to 0. That's everything above the x-axis. Y is greater than or equal to 0. That is everything. This is everything to the left of the y-axis. This is everything above the x-axis. That gives us this and that. Okay, that's what the last two give us. Those are the x and y axis. So on my feasible region, this is one of the things that's really important is you graph, these are my constraints. I graph my constraints. These are the parameters of what I'm trying to do. I can't be more or less than this. I can't be more or less than that. These are my constraints that I have on my system that I'm trying to work with. My feasible region is everything in here. Okay, now I'm not getting carried away coloring it in, but that's my feasible region, that little house-shaped object inside the middle there. Okay? What that feasible region gives me is the possibilities for the maximum or minimum of this. This is what I want to try to maximize or minimize. I want to find the maximum P or the minimum P. In this case, this might be profit. Okay, this is typically used in an economics kind of setup. That's what all your example problems are. And so P would be profit, how much money you're going to make. You want to maximize that or minimize it. What's the minimum I'm going to do? You don't want to get into a job, you don't want to get into building something where your maximum profit is 0, because then you're never going to make any money. But if you have something where your minimum profit is not a negative, but you're guaranteed of making money, that's not a bad thing either. You kind of want to know, what's the best I can do, what's the worst I can do? And that's what max and min tells you, what's the best, what's the worst. Those are the two things you're always looking for. You will most likely fall somewhere in between, but you want to know the best and the worst. Okay, and that kind of makes sense. So what I have to do is I have to find the x's and y's to put into here. What I get, those are the x and y's that I plug into here are the coordinates of my vertices. So right here, this is one of my vertices. Every corner. 0, 0 is one of my vertices. It's one of my possible max or mins. I don't know if it's maximum or minimum. I will have to try it. I will have to try all of them. Okay. This corner right here, 0, 2. This corner right here, 6, 0. And this one here would be 6. X is 6. And that looks like 1, 2, 3. Yeah. This one here. 6,3. And this one, the graphing could probably be a little bit better. It's not going to be like, 3.1 and 2.5. It's going to be on a vertex. Okay, I guarantee it's going to be on one of those crosshatches. There's going to be a whole number of ones that you're dealing with. It's awfully hard for me to graph with the marker up here, but everyone that you do, it's going to be on a vertex. Going to be on a corner. So this would be the point 3, 1, 2, 3, 4, 5. 3, 5. Those are my 5. And I've got 5 because how many vertices do I have? I've got 5 vertices. I have 5 points I need to test. I'm going to try them all one at a time. Which one gives me my maximum P? Which one gives me my minimum P? So I try them one at a time. So I try P 0, 0. Notice what I did there? I did a little subscript of the coordinate, P at the point 0, 0. So I know which point I'm doing it at. 2 times 0 plus 3 times 0 is 0. I am guessing that is my minimum, because there's no way to get a negative. So that's got to be my minimum, but you'll always want to double check and make sure. But you try every point to make sure that I get all of them. Pick one and go either clockwise or counterclockwise to go around until you get back to it. I'm going to go clockwise, so my next point is 0, 2. Point 0, 2. 0 for x, 2 for y. 2 times 0 plus 3 times 0 is, 3 times 2, my bad, is 6. Okay, you with me so far? Try the next point going around, which would be 3, 5. The point 3, 5. 2 times 3 plus 3 times 5. 6 plus 15 is 21. And then I want to try the next number, 6, 3. P 6, 3. 2 times 6 plus 3 times 3. 2 times 6 is 12. 3 times 3 is 9. 9 plus 12 is 21. Interesting. And then the last point, P 6, 0. 2 times 6 plus 3 times 0 is 12. Try them one at a time in your equation you're trying to maximize or minimize. Where do I have a minimum? 0, 0. What is my minimum? I have a minimum of 0 at 0, 0. Because that's my smallest P is 0. There's no other smaller value of P. What is my maximum? What? What's my maximum? 21. At where? I have 2 of them, don't I? At 3, 5 and at 6, 0. Right? Oh, sorry, 6, 3. 3, 5 and 6, 3. It's possible that I have a max, the max, or the minimum happens at more than one place. What this means is, let's say I'm selling t-shirts and sweatshirts. My best profit would be 3 t-shirts and 5 sweatshirts, or 6 t-shirts and 3 sweatshirts. Okay? That's kind of where I'm looking at. One of those two things is going to do the best for me. Any other combination will not give me my maximum. Does that make sense? That's what we're looking for. Only the vertices will give you your maximum. Only your vertices will give you your minimum. What we're doing here is looking for the important points. What are my important places? There are several ways and several. So one of the things mathematics will do for you is narrow things down. So I'm not looking everywhere. I'm just looking at the possible places where the important things can happen. This is one of those ways where you can find where do the important places happen. Because there's technically an infinite number of combinations of x and y that work that system. But the only ones where something important happens are at the vertices. Okay, that's the only place where the big things that we want to have happen can happen at the vertices. There's technically an infinite number of x-y combinations, but only the vertices are the only ones we're interested in, because that's where the best or the worst will happen. Okay. Your turn. Graph those constraints. Find the vertices. Figure out which vertice will give you a maximum and minimum value, and what those max and minimum values are. Okay, let's do these. So the first one, 2x plus y is greater than or equal to 12. My y-intercept is 12. I do think I have that on here. 1, 2, 3, 4, 5, 7, 8, 9, 10, 11, 12. Ooh, good. And 1, 2, 3, 4, 5, 6. Ooh, that was horrible. I can do better than that. I can do so much better than that. Yeah, that's better. Okay, second one. Ooh, and I want to test it. Put in 0. 0 plus 0. Is 0 greater than 12? No, so it doesn't change the side. It does it on that side. Second one, x is between 3 and 8. Here's 8. Here's 3. And it's everywhere in between those two. And y is between 2 and 6. There's 2. And 3, 4, 5, 6. And it's everywhere in here. So our region, and this is one where you have to be careful on. Students, you got to be careful where you do this. It's between these two, so I have along in here, along in here, along here, and along this line here. It's this little space inside there. That's my feasible region. Okay. So my x's and y's are actually aren't that hard to get for the most part. Okay. This one down here, let's see, the x is 8 and y is 2. 8, 2. This is the point 8, 6. This is the point 3, 6. And then this one here, 3, 4, 5. That point right there is the point 5, and y is 2. It's nice when you have the horizontal and the vertical lines. Makes your constraints easy. The diagonal ones are the ones that come sometimes hard to read. So those are my vertices. I've got 4 of them. I have to test all 4. Okay. So start down the bottom corner. 5, 2. 3 times 5 plus 4 times 2. 15 plus 8 is 23. Going anti-clockwise this time. 8, 2. 3 times 8 plus 4 times 2. 3 times 8 is 24. 24 plus 8 is 32. Continuing around anti-clockwise. The 8, 6. 3 times 8 plus 4 times 6. 3 times 8 is 24. 4 times 6 is 24. I get 48. And then last but not least, 0.36. 3 times 3 plus 4 times 6. 9 plus 24 is 32. Okay, where's my minimum at? What is my minimum? My minimum's 23. At the point 5,2. It's important you understand identifying both of them. What is the maximum? What is the minimum? And where they happen are two different things. Where and what are two different things. Where it happens is the coordinate. What it is the number it actually is. My maximum is 48. At the point 8,6. You will be asked, what is the max? Where is it? What's the min? Where is it? There's a difference between the two. Where and what are not the same thing. Where is the coordinate? What is the number? You'll have to be able to identify both of them. Okay. Questions on this before we move on? Okay. So this last one is actually just determining the constraints. It's not actually solving it. We're not going to graph it. But this is an example of where the constraints would be coming from. So your company is screen printing T-shirts and sweatshirts. You have at most 20 hours to make the items. It takes 10 minutes to print a T-shirt and 30 minutes to print a sweatshirt. You do not want to spend more than $600 for supplies. It costs $4 to produce a T-shirt with a $6 profit, $20 to produce a sweatshirt with a $20 profit. You want at least 50 items available to sell. Determine the number of T-shirts and sweatshirts. What is your maximum profit? First thing I have to do is pick two variables. Okay. So X and Y are what we've been working with. I do not need to use X and Y. I can come up with any two variables I want. I would come up with T-shirts and sweatshirts, T and S. T and S. Notice I put a little Y in through my S. Why? Yeah, because it looks like a 5, otherwise I get confused. Okay. Now I need to come up with my equations, my inequalities that are my constraints. You have at most 20 hours, to make the items. That's a constraint. I don't have more than 20 hours to work. That's a constraint. That's a limit on my time. It takes 10 minutes to print a T-shirt and 30 minutes to print a sweatshirt. Okay. Before I write this equation, remember, I have to have my units have to match. 2 hours, 30 minutes, 10 minutes, they don't match. Now I have a couple of choices. I can either take minutes and make it hours, and 30 minutes, that's easy. That's a half an hour, right? But 10 minutes is how much of an hour? It's 1/6 of an hour. Hard to do as a decimal. It's much easier to take 20 times 60. What's 2 times 6? 12. And then I have 20 and 60, so I have to put 2 zeros on the end. So that means 10 minutes per T-shirt plus 30 minutes per sweatshirt must be less than or equal to 1,200 minutes. That's my first constraint. Does that make sense? I have a limited amount of time. How much time I spend on T-shirts, how much time I spend on sweatshirts, combined together has to be less than a certain amount. That is a constraint. I can spend less than that. I can go exactly how much time. I cannot go more than that. The next constraint is you do not want to spend more than 600 for supplies. Okay. It costs $4 to produce a t-shirt and $20 to produce a sweatshirt. So my constraint, how much it costs for the two of them, must be total less than 600. So for T plus 20S must be less than or equal to 600. You want at least 50 items to sell. At least. Notice my constraints. My constraints are all at most or at least. Those are constraints. Constraints are written as inequalities. At most this, at least that. That's what your constraints would always be. So I can only make 50 items total. That means the number of t-shirts plus the number of sweatshirts must be less than or equal to 50. Or sorry, it must be greater than or equal to 50, because it says at least. Those are my constraints. How much it costs, I only have so much money to spend on materials. I only have so much time to spend doing this. I need to make a minimum number of items. What am I almost always trying to maximize? Profit. That's the name of the game, right? You're in business, you're trying to do something. What do you want to do? You want to maximize profit. Okay. So I make profit by selling t-shirts and selling sweatshirts. The thing I'm trying to maximize is my profit, and I make $6 per t-shirt, and I make $20 per sweatshirt. So we are not going to do this. However, if we were doing the programming, we would graph these, find the vertices, plug them into that. That would tell us our best combination to do. What's the best thing to do that's going to make us the most money? What combinations of t-shirts and sweatshirts is going to make us the most money? That's the idea behind it. So you can kind of see, when you look at this problem, you can see where that is a useful thing to do. Okay. Questions?